Okay, it's another session of trying to solve problems from the book, Problem Solving Strategies, from the chapter called The Invariants Principle. I've now reached, I think it was number 50 out of 60. I have a time limit of just over an hour, which is always slightly problematic because I don't know if I'm going to get ambushed by a hard problem if I start one, say, with 25 minutes to go or something. So I'll just hope for the best. If I look at one and it looks hard, I might just not take the risk. So let me go though, because of the time limit, as quickly as possible. And let me see what the next question on the list is. It starts with the promising words, a dragon has 100 heads. A knight can cut off 15, 17, 20, or 5 heads. "15, 17, 20, or 5 heads." Then a mysterious word, respectively. Not quite sure what that's respecting, but with one blow of his sword. I'm sure that will be important. In each of these cases, here comes the respectively. So I think the word respectively was premature, but is sort of relevant. 24, 2, 14, or 17 new heads grow on its shoulders. If all heads are blown off, that's slightly mysterious because I thought they were being cut off, but there we go. The dragon dies. Can the dragon ever die? Well, let's not be too mathematical about it and say, well, it depends whether there are any other ways the dragon could die and things like that, but we all know what the question means. So, let's just think about, I think if you cut off 15, you add 24. If you cut off 17, you add 2. If you cut off 20, you add 14. And if you cut off 5, you add 17. And what is the effect of all that? So minus 15 plus 24 is adding, the net effect is adding 9. Here the net effect is adding 15. Here the net effect is subtracting 6. And here the net effect is adding 12. What do I notice about those numbers? They're all multiples of 3. But wait a minute, that's not quite enough. What do I notice about 100? It's not a multiple of 3. However, if we got down to, say, 17 heads and then cut them all off, then the dragon would die. But what do we notice about the numbers 17, the ones that are not multiples of 3, so 17, 20, and 5, they're all 2 mod 3. So to get to a point where with one final blow you can get rid of cut off all the remaining heads, you have to have a number of heads that is either 0 mod 3 or 2 mod 3. So if there are 15 heads, then it's 0 mod 3. If there are 17, 20, or 5 heads, there are 2 mod 3 heads. But with each with each blow, you don't change what it is mod 3, and 100 is neither 0 nor 2 mod 3. So the answer is no, and that was a rather simple mod 3 question. So let's move on. 52. Is it possible to arrange the integers uh, 1, 1, 2, 2, all the way up to 1998. I presume the question was originally devised in 1998, such that there are exactly I minus 1 other numbers between, this looks more interesting, any two i's. Oh, I see. So between the two 1998s, you want to have 1997 numbers, and we've got twice 1998 to play with, so there's no sort of obvious difficulty there. So this really does look like something where we're going to have an invariant. But what sort of invariant could we have? The perennial question. So if the numbers are A1, A2, up to A3996, which is twice 1998, then I feel that I want to look at some sort of invariant, and a natural kind of invariant would be something of the form sigma lambda I ai. Now what do I mean by an invariant? I think I mean something where I can yes. So I have a kind of guess in mind. So if I take all the lambda i's to be 1, then there's no hope, because however I permute it, I'll get the same answer. But something that worked for another problem, it feels as though it's got a good chance of working for this, is to look at sigma, another problem in this series. So sum from 1 to 3996 minus 1 to the I ai. So in other words, minus A1 plus A2 minus A3 plus A4. Now the point about this is, that makes it promising, is that the fact that there are exactly I minus 1 other numbers between any two i's tells us that if I is odd, then the ai, they'll have an even number of numbers between the two occurrences of ai, in which case we'll get a contribution of, so for I odd, we get plus or minus, unfortunately, 2 ai. And if I is even, then there'll be an odd number of numbers between, in which case we get 0. That seems significant. What else can we say about this permutation? I feel as though it's going to have something to do with parity, or maybe mod 4, because that means that the whole sum is going to have to be even. But I think that's clear anyway, because each AI, each number between 1 and 1998 occurs twice, and either plus or minus, so we're certainly going to get something even. But can we somehow argue that, so if we get plus or minus 2 AI, and AI is odd, so we get plus or minus 2 mod 4, and how many odd numbers are there between 1 and 1998? It's 900 and looks like 999 of them, because 1998 is twice 999, so there are yeah, so 999 odd numbers. From 1 to 1998. So this thing here is going to be congruent to 2 mod 4, because if you've got an odd number of numbers that are 2 mod 4, then their sum will be 2 mod 4. So can I argue somehow that I cannot make something that's 2 mod 4? I'm not sure about that, but let's just think. So a contribution from each odd number, if I've got a choice of whether to make it plus or minus. And now I've got a choice of where to put it. So wait a moment. So I have 1998 minus ones and 1998 plus ones. What is the sum of the numbers from 1 to 1998 mod 4? How easy? Okay. Let me just do it in a slightly cheating way. So 1, 3, 6, 10. No, I'll do it like this. So the sum of the numbers from 1 to 1998 is 1998 times 1999 divided by 2. Just check, yes. Which equals 999 times 1999, which is congruent to what? Mod 4. Well, it's certainly odd, which is sort of promising. And maybe that's the point, actually. I think that is the point. I think that's all I need to say. So I was overcomplicating things by saying it was 2 mod 4. We get that the sum must be even because of this assumption, because the odd, just a moment. No, sorry, we know that the sum is even. That's not interesting. So what is it mod 4? So 1000 is 1 mod 4, so that's 3 mod 4, and that's another 3 mod 4, and 3 3s mod 4, so that's congruent to 1 mod 4. And if I'm now allowed to change some of those numbers, it seems as though, so if I change some of the signs, wait a moment, sorry, yes, so but I'm taking this sum twice, so I get 2 mod 4. So sum AI is congruent to 2 mod 4. Each time I change the sign of an even number, it will not change the sign of the sum. And each time I change the sign of an odd number, it will change the sign. Okay, I think I may have got there. So if I change, not quite what I'm expecting, but if I change the sign of an odd number, the sum mod 4 changes by 2, because we've gone from sort of AI to minus AI. If AI is odd, then the difference is 2 AI, and twice 3 mod 4 and twice 1 mod 4 both equal to 2. So the sum changes by 2, but we know that we change the, because each odd number is separated by an even number of numbers in between, we know that the number of odd numbers changed is even. That's not what I wanted, though. Oh, but it's not what I get. Wait, let's go back to the question. There are exactly I minus 1 other numbers between any two i's. So if I is odd, I get an even. Oh, so I think I've done something stupid here. Say I have A3, then there have to be 2 numbers between that and the next occurrence of A3. And so actually they are an odd distance apart. So the odd one contributes 0, and the even contributes 0 as well, because we have, say, A4, an odd number of numbers in between, and A4. So I either get A4 plus A4, or I get minus A4 minus A4. Either way, it'll contribute 0 mod 4. So this sum, I may just made a stupid mistake. So actually this sum, which makes the question easier now that I've got it right, that sum is 0 mod 4, but the number of odd numbers changed. Let's get this right now. I think everything is just sort of the wrong way around, so let's cross all this out. So for each odd number, I have to choose a plus one sign for one of them and a minus sign for the other. There are 999 odd numbers from 1 to 1998. So number of odd numbers changed is odd. So and original sum, sorry, I shouldn't have crossed it all out, is 0 mod 4. Changing an even number makes no difference. I mean, putting a minus sign in front of an even number changes everything by 0 mod 4. So final sum is 2 mod 4, and that's a contradiction. I'll just check whether I really understand what I've just done. So I'm calculating the sum of these things, and on the assumption that we have exactly I minus 1 other numbers between any two i's, I get that for any odd number, like sort of 5, I'm going to have 1, 5, and 1 minus 5. And for any even number, they'll have the same sign. And so that means that the sum is going to be 0 mod 4. But another argument says that because every odd number occurs with one plus sign and one so the other argument says that the sum of all the numbers, sort of the sum of all the numbers is congruent to 0 mod 4. Each time you change the sign of an even number, it doesn't vary. Each time you change the sign of an odd number, it varies by 2 mod 4, and we've changed the sign of an odd number of odd numbers, and so we get 2 mod 4. So two different arguments. One says that that this sum here must be 0 mod 4, and another says it must be 2 mod 4, and therefore we can't do it. That was silent. How am I doing for time? I've got time for another question, unless it ambushes me. Slightly irritating to waste a bit of time on that question because of that daft mistake, but the following operations are permitted with the quadratic polynomial ax squared plus bx plus c. A, switch A and C. B, replace x by x plus t. Where t is any real. I quite like the sound of this so far, but what's the question going to be? By repeating these operations, can you transform x squared minus x minus 2 into x squared minus x minus 1? Well, one little thought here is that if you start with ax squared plus bx plus c and you switch a and c, then whatever roots you had of the original polynomial become, you end up taking the reciprocal of those roots. So what I mean is that ax squared, assuming that let's not worry about 0 for the moment, ax squared plus bx plus c equals 0 if and only if c x to the minus 2 plus b x to the minus 1 plus a equals 0. And as I say, it's slightly more complicated if there's a 0 root. So if c were 0 here, just going on there. I'll come back. There may be a small problem with 0, but I think that there shouldn't be too much of one. But another fact is that if you replace x by x plus t, that's just going to shift the roots backwards by t. Otherwise, it'll subtract t from the roots. So I'm wondering whether one of these has one root and the other one has two roots, in which case I think that would more or less knock this question on the head. But what is the... so that one is x plus 1, x minus 2. And this one is, looks like the golden ratio, so it's got two roots. And there'll be 1 plus or minus the square root of 5 all over 2. So that doesn't do it. But if we think about the difference between the two roots, does that do anything? So if x minus y equals... So I'm just wondering now whether the fact that the roots here are extremely rational and the roots here are extremely irrational could make a difference. So shifting by t won't change the difference of the two roots. But what happens if I take the reciprocals? So if x minus y equals r, then 1 over x minus 1 over y equals y minus x over xy equals minus r over xy, but that doesn't seem to... I could quite happily shift x and y by something and make this number extremely irrational, so I don't see a problem there after all. Now there is another small point, which is that it may not be enough to look at the roots. It may also be important to, if I multiply this polynomial by a scalar, it'll have the same roots, but it's not clear that I can multiply by a scalar, so to speak, using these sorts of operations. So it looks to me as though using a combination of taking reciprocals and translating, I can in fact turn any pair of real roots into any other pair of real roots. I just move them to a certain point where when I take the reciprocal, their distance will be what I want, which I think I can probably do by the intermediate value theorem. And then once I've got the roots to be at the right distance apart, I can then shift them. So that was a useful exercise to think about that, but it doesn't solve the problem, but it tells me that it gives me information, or gives me a restriction on what the solution could look like. I'm assuming it's impossible, of course. So the invariant, it's going to, I think I better just see what happens when I substitute in x plus t into this thing. So I get I think I need to look more for an invariant of the coefficients rather than an invariant of the roots. So that equals ax squared plus b plus 2ta x plus c plus bt plus at squared. I don't really need the brackets there, but so what has, I want something that's remained the same. So in other words, if I take the numbers a, b, c, and a, b plus ta, c plus bt plus at squared, I want some quantity associated with those not to have changed. Ideally something reasonably symmetrical, so I'd also like CBA to have the same invariant. So it's very tempting now actually just to look at the discriminant. I don't know why I'm just because it's such a natural invariant associated. I don't think this is going to work, but it seems a bit silly not to look at it. So b squared minus 4ac, and what about this? So I'll get b squared plus 2bta plus a squared t squared minus 4 a c plus bt plus at squared. Okay, looks like it is working embarrassingly. Or is it? No, maybe not. So what does that equal then? It equals b squared minus 4ac. But what else? I've got 2bta minus 4bta, so minus 2bta, and then plus a squared t squared minus 4a squared t squared, so minus 3a squared t squared. So not totally surprisingly, that didn't work. But could it have been made to work if I'd done something slightly different? Like, what if I'd taken b squared minus 2ac or something like that? So b squared minus 2ac, then I'd have got the 2bta to cancel with a 2bta, but unfortunately a squared t squared doesn't cancel with a 4a squared t squared. But let me just quickly think about that, because I'm not absolutely 100% convinced that that's useless, because I just no, something's peculiar here. By the way, the reason one of the reasons I quite like that is that it's symmetrical in A and C, so it definitely doesn't change if we swap A and C around. But what I'm thinking about is whether we can get something to be always positive or something along those lines. Actually, I'm not quite sure what what I really think I'm trying to say there. How can I get the, so my question really is how can I get the t's to cancel out of all this? So what expression can I make that's symmetrical in A and C and gets rid of all the t's? Actually I'm going to say I can certainly use the sum of these two, so I can use as I wish a plus c plus bt plus at squared, and I can also use the product, which is ac plus abc, sorry, ac plus abt plus a squared t squared, and I'm trying to get rid of the TA, so why don't I simply multiply this one by A? Oh, but then it's not symmetrical. So that's slightly interesting. But and I was also having b plus 2bta plus a squared t squared. So I'm just going to sort of write down things that I can generate. So out of these, I can generate b squared minus ac plus abt, getting these to cancel. But I don't see what to do to get rid of this last remaining t. What am I'm just trying to work out what it is exactly that I'm trying to do. I think I'm trying to find a polynomial in the coefficients that's invariant and it's symmetrical in A and C. That seems to be roughly the long and short of it. So an alternative would be to get this 2b ta to cancel, so I could go for 2b squared minus, sorry, b squared minus 2ac minus a squared t squared. This is the thing that intrigues me. I must be doing something slightly silly somehow, but if my invariant is, supposing I tried b squared minus 2ac, then after I've done the add t operation, it becomes b squared minus 2ac, and this thing cancels with two of these. And then I end up subtracting a squared t squared. But if I then go back in the other direction, why doesn't it mean I subtract a squared t squared again? That I don't understand. I think I must be making a mistake somewhere, so let me try to work out what that is. I've definitely got an AT squared here, and a BT and a C. I've definitely got a BX, and here I've got a 2x T times A. That really does seem to be... Oh, I did a mistranscription from here to here. I forgot to put a 2 in there. Okay, let's go back to the discriminant again. So it's b squared plus 4bta plus 4a squared t squared minus 4ac minus 4abt minus 4a squared t squared. So the discriminant was an invariant. I feel very, very silly there. Just one stupid mistake copying something from one line to the next meant that I spent a long time trying to puzzle what to do, given that the discriminant was not the invariant I was looking for, when in fact it was the invariant I was looking for, because presumably the discriminants of these two are going to be completely different. Yes, because, well, they certainly are. B squared minus 4ac can't possibly be the same between those two. Okay, that's it. I've done 2 questions in a row where I've been held up by daft mistakes. I better be a bit more careful. Have I got time for another one? I think I'm actually not going to take the risk. I might as well just keep this as a short video. So I've done 3 questions there. It was slightly shambolic, but and the first one was boringly easy. I'll make that my ration for today.